I think it's a good idea to talk about what's going on here. Let's do this with a different kind of example. Suppose I tell you that t is a linear transformation, t of 1, 2 equals minus 1, 3, and t of minus 2, 1 equals 2, 0. Unlike the previous example, this doesn't give an explicit definition of t. Even so, we have all the necessary information to determine everything about this function. What is t of 2 for? If t were just some function, we would have no way to determine this. But t is linear. Notice 2, 4 is 2 times 1, 2, and we know t of 1, 2. Therefore, t of 2, 4 is t of 2 times 1, 2. Pull out the 2, since t is linear. This becomes 2 times minus 1, 3, which is minus 2, 6. How about t of 5, 5? This is no longer just a scalar multiple of one of the vectors. Instead, we need to write 5, 5 as a linear combination of them. Set up a matrix and reduce. So 5, 5 is 3 times 1, 2 minus negative 2, 1. Therefore, t of 5, 5 is t of 3 times 1, 2 minus negative 2, 1. Distribute the t and evaluate. So t of 5, 5 is minus 5, 9. More importantly, 1, 2 and minus 2, 1 span R2. So we can find t of any vector a, b. So how does this tie into 1 to 1 and onto? Well, if t is a linear transformation, then t of 0 equals 0. This might be a homework problem. If t is also 1 to 1, then if t of anything equals 0, that anything must be 0, because 0 can only be hit once. If t is 1 to 1, and t of c1 v1 plus ck vk is equal to 0, then we must have had c1 v1 plus ck vk equals 0. You should see the connection here to linear independence. On the other hand, if t is onto, then for any vector y in Rm, we can write t of c1 v1 plus ck vk equals y. Expand the left-hand side, we get c1 t of v1 plus ck t of vk equals y. In other words, t of v1 up to t of vk span Rm. This is exactly the same as the columns spanning Rm. Neither of these are full proofs, they're missing little details here and there. I recommend going through them, try to make these perfect.